Today we're going to demonstrate the usage of the shard Rebalance API, which was introduced in version 3.10. And this API will be helpful whenever the shards of your cluster deployment are not evenly distributed across all cluster nodes. We're going to start with a cluster consisting of 3 coordinators, 3 DBServers, and 3 agents. When I move to the shards view, we can see that I have created a few sample collections, and all of those collections have 9 shards and a replication factor of 3. So each shard consists of 1 leader shard and 2 follower shards. As you can see, DBServer 2 is only serving as a follower for this specific collection. Earlier, I have simulated an outage of DBServer 2, and as a consequence of this outage, all leader shards, which were previously located on DBServer 2, were relocated to one of the followers, so either to DBServer 1 or DBServer 3. The UI also offers a more general shard distribution view, which is accessible via cluster and distribution. Right here we can see that the total shard distribution is quite even across all 3 nodes. However, at the same time, due to the outage of DBServer 2, we can see that not a single leader shard is located on DBServer 2, and it's holding way more followers than the other ones, which is quite bad with respect to the load distribution. In order to improve the shard distribution, we can make use of the Rebalance API. As the documentation states, there are 3 different types of shard moves. The first one is switching the leadership of one shard between its current leader and an in-sync follower, which is a fast and low-cost operation. Moves of type 2 are moving the data of a leader shard to a new DB server and reassign the leadership. Type 3 moves are moving the data of a follower to a new DB server and make it a follower. As moves of type 2 and 3 require to copy shard data over the network, they are slow and rather expensive. Using this API, you can activate or deactivate any of those move types independently. By default, only the move of type 1 is activated, and moves of type 2 and 3 are set to false. Next, let's jump to the API execution. With a GET request, you will get an overview of the current shard distribution, and you will compute the so-called imbalance score, which is a score that displays the quality of the shard distribution. Additionally, it will also show you the amount of ongoing and pending move shard operations. A post request to the same API path will compute a set of move shard operations to improve the current shard balance. Adding an additional execute to the API path will give you the option to pass a set of move shard operations and directly execute those on the cluster. And finally, there is also a put variant, which will not only compute a set of move shard operations, but also immediately execute those on the cluster. Going back to our cluster scenario, we have seen an even total shard distribution, but quite a big imbalance with respect to leader shards and follower shards. In this case, it is sufficient to only consider moves of type 1, which change the leadership between a leader and a follower of a shard. Let's see the API in practice. We are going to start with a GET request pointing to one of our cluster's coordinators, and we are going to use the default API options. The result looks as follows. We see a leader object referring to the leader shards of the deployment, and this one is containing the current leader shard distribution, our target leader shard distribution, and most importantly an imbalance score, which is representing the current quality of the leader shard distribution. The lower the imbalance score, the better the distribution is. We see another object named shards, which is containing both leader and follower shards. Again, we see the current shard distribution, our target distribution, and an imbalance score representing the quality of the total shard distribution. On the bottom, we also see the amount of pending and ongoing move shard operations. As a next step, we're going to run the same request, only replacing the GET with a POST. As mentioned earlier, this will compute a list of move shard operations to improve our cluster balance. In addition, the response contains two new objects. The first one is called imbalance before, which is representing the current shard distribution, including imbalance score for leaders and imbalance score for total shards. The second new object is called imbalance after, which is representing the shard distribution once we have executed all the shard moves listed in the moves object. Right here, it is quite obvious to see that the imbalance score of the leader shards would have been drastically reduced once we executed the shard moves. As a final step, we're going to run the same command with a put instead of a post. Executing the put request will only trigger the rebalance operation. It will return while the rebalance operations are still ongoing. In order to check the current status of the rebalance operations, we can make use of the get request once again. As a reminder, we have only executed fast move operations of type 1. In the get output, we see that there are no current pending move shard operations or ongoing move shard operations. Going back to the UI, we can see that we are done, since we achieved a good leader shard distribution and a good follower shard distribution across all nodes. Of course, fixing shard imbalance won't always be that easy and fast, and that's why I want to continue with a slightly more complex scenario. Right here, I have added a fourth DB server. It's currently empty and doesn't hold a single shard. Move operations of type 1 won't help here, and that's why we need to make use of type 2 and type 3 move operations, which copy the data over the network and reassign the shard ownership. In order to achieve that, we need to add two additional parameters to the API call. As previously shown in the documentation, moves of type 2 and type 3 are deactivated by default. In order to activate those, we need to set move leaders to true and move followers to true. Once we run this command, we will again compute a set of move shard operations and immediately execute those as we're using the put variant. At this point, the shard move operations are triggered. We can monitor the progress of pending and ongoing operations via the get request. As you can see, the pending move shards are slowly decreasing. After some time, we can observe that all pending shard move operations have been processed. Once again, going back to the UI, we can observe that a good shard distribution, including new DBServer 4, has been achieved. I would like to end with a few final remarks. When you make use of the Rebalance API in your own cluster environment, it might happen that you do not achieve a perfectly even shard distribution. By default, a single rebalance iteration will consider at most 1,000 shard moves. This value is configurable and capped at 5,000. So, in case your cluster is holding a lot of shards, you might simply have to call the API multiple times. Another potential reason might be that your cluster is holding a lot of coupled shards. A common example for that is a one-shard database, where each leading shard is located on the same DB server. In such a case, it is not possible to move a single shard, but only the entire shard group at once. Finally, I would like to point out that rebalancing operations apply additional load on the cluster. You don't have to worry about type 1 moves, as they are cheap and finish within seconds. However, moves of type 2 and 3 are way more expensive, as they need to copy data over the network. Therefore, it is recommended to schedule a maintenance window for those moves whenever minimal cluster load is expected. Thank you for listening.